Hello, everyone. I'm Abhinav. I used to be a computer scientist at Lawrence Livermore until last year. I spent about 8 or 9 years at Livermore, and then last year I moved to the University of Maryland as an assistant professor. And today I'm going to talk about a performance tool that we developed at Livermore, and we're still developing collaboratively with them, which is for performance analysis. It started as a tool that was developed at Livermore, but over time, especially this summer, we had several summer interns from different places contributing to it. It's an open source tool. So we have students from UC Davis, University of Tennessee, Knoxville, and Arizona working on it, and I have some of my students working on it. The tool is called Hatchet, and we look at how we can analyze calling context trees or call graphs using Hatchet. So as we write parallel programs in high performance computing, I'm sure all of you know, understanding performance bottlenecks is critical to optimizing HPC codes. Profiling and tracing tools can help us identify what parts of the code consume the most time. So here are two GUIs, one from HPC Toolkit. This is the HPC-T view that shows gprof data here. And then the other one is trace data in Vampire. And you're looking at how much time do you spend in different functions. Many tools also provide the file and line numbers for different functions. And you can try to trace performance problems to specific parts of the code. Since I'm a PPLer or ex-PPLer, I think I can throw some light banter. So if you're sick and tired of looking at traces from projections, I think this is a good talk to look at. And hopefully I can convince some of you to start looking at some other tools. So one of the main things people want to do when they're looking at performance problems or bottlenecks is they want to attribute performance or time to code. This requires a reasonable understanding of the code structure. So you need to understand where does the control flow start, what functions are called, and what subsequent things get called, and so on. There are many sophisticated profilers that can attribute time to calling contexts. Some examples of measurement tools are HPC Toolkit, and hopefully John will talk about HPC Toolkit in his keynote today. Caliper is a tool that comes out of Lawrence Livermore. Scorpy, Tau, gprof, they're all of these are tools that you can use for looking at performance profiles. When we started working on Hatchet, one thing we noticed was that there was a limitation in the current analysis portions of these tools. One, they only support their own unique formats, and also they have limited support for saving or automating the analysis. So once you do an analysis for one data set, if you wanted to do a similar analysis on another data set, you have to load it back, follow the same steps again, and do it. Most tools only support viewing one data set at a time. So if you have to compare two timelines, you have to pull up two projections or two HPC viewers and then look at them side by side. Finally, most of these tools do not have any programmatic way of analyzing the data. So there's no way to write small programs or scripts to read the data in and do some analysis. And that also boils down to having a lack of capabilities to sub-select and focus on specific parts. And that's where the idea of Hatchet was born. But before we go into that, let me just give some definitions of the kinds of data that the Hatchet tool focuses on. So we focus on data that's a hierarchical context. So for example, calling context trees is one example. Calling context trees represent different call sites in your program, and all the functions that the control flow had to go through to get to those leaf nodes. So for example, we see here that program execution starts in foo calls some other functions, and so on. And finally, you reach those leaf nodes that are baz and grolt and so on. Now, each of those, let me see if there's an animation here. Yeah. So each of these paths from the root to a specific leaf node is called a call path. And that gives you a calling context for where was that call site called. Different profilers will store different amount of information on each node. So you might have the file and line number, function name, call path. You might have load modules, the process ID, thread ID, and so on. Typically, tools will also have performance metrics. So you would have the most common one is time. So many tools will store the inclusive time and exclusive time for each node. You might also have other metrics if you enable, let's say, PAPI, and you have number of flops or cache misses, etc. Now, you can go from a calling context tree to a call graph by merging all the nodes that have the same name. So for example, in this case, we see here that the node in maroon, that's Garply, is called multiple times. So if you merge those nodes into a single node, you now get a graph where a node might have multiple parents depending on what functions we're calling it. Hatchet handles both of these kinds of data. We do not handle traces currently, although that's something we are considering. If we can have, if there are traces that have hierarchical calling context, but currently we only handle performance profiles where the data has been aggregated over the entire execution. So this is where, like, looking at the shortcomings we found in the analysis tools in HPC, that's where the idea of Hatchet was born. We wanted to create a Python-based library that enables users to do programmatic analysis. The main idea in Hatchet is to have an in-memory representation of your call graph or calling context tree. The other key idea is we leverage this Python library called Pandas, which supports multi-dimensional tables. The novel thing we have done in Hatchet is we connect the graph to the pandas by using the nodes in the graph to index into the data frame. So we use a structured index, that's the graph, and that's used to index individual rows in the data frame. And then once we had this central data structure in Hatchet, we added a set of operators that we think are common operations people do on, or people might want to do on performance profiles. So we add functions to filter and prune the tree and aggregate profile data in various ways. We have also added operators that help you compare data sets from multiple executions. Please feel free to ask questions in the middle, or raise your hands, or add comments in the chat, and I can answer them as I go. So just a quick intro to what Pandas is. Pandas is an open source Python library. It has a main data structure called a data frame. This is a two-dimensional tabular data structure. It supports many operations borrowed from SQL databases. In the data frame, there are rows that are used to store different entries in the data frame, and columns might store different values for each row element. By default, each data frame has an index. You can also have multi-indexes in data frames, and we use that because each node might be collecting data for multiple MPI processes, and for each MPI process, there might be multiple threads. So we use a multiple index to store data in a hierarchical format for each node, MPI process, and thread ID. Okay, so what's the main data structure in Hatchet? It's a graph. This is an in-memory graph where we read in the data from our input data files, which might be from HPC Toolkit or Caliper. Each node is assigned a unique key, which enables using these nodes as index in the data frame. Each node also has a frame that describes the code it represents. So some profilers might have complicated or might have complex node types, where a node can be a function, or it can be a loop, or it can be a statement node. So we store that information in a frame, and the frames don't have a rigid schema, so you can change what you store in the frame. The nodes define the structure and connectivity of the graph. So a parent might have multiple children, a child might have multiple parents, and it defines the caller-callee relationships between the nodes. And then we connect the node to a data frame. So the central data structure in Hatchet, which we call a GraphFrame, has two parts. It has a structured index graph object, and then it has a pandas data frame. As I said, the graph stores the caller-callee relationships, and then the data frame stores all the numerical and categorical data. So this is what the graph might look like. And then for each node in the graph, let's say we have main as a node, that particular node will point to a particular row in the data frame. And on that node in the data frame, we store all the both non-numeric or categorical and numeric features. So you might have time, inclusive time, the name of the node, file and line number, and so on. Okay. Now, when there are metrics per MKE process, each node has multiple rows in the data frame. So for example, if you have two ranks that you are running your program on, then as you can see here, now instead of having a single index, which is just the node, we have a multi-index that's node comma rank. If you also have threads, it will be node comma rank comma thread. And then for each node, so program root here has two MPI ranks, 0 and 1, and different data, especially in terms of the numeric metrics, different data might be stored for each MPI process. Typically, the file and line numbers and modules for these SPMD programs are all same. They're all same for these same MPI ranks or different MPI ranks. Now we have immutable semantics for graph nodes. So anytime, since we are using the graph nodes to index into the data frame, any operation that modifies these graph nodes in place creates a new graph frame, so that we don't index incorrectly into the data frame. And we implement this using copy on write semantics. So every time we want to write to the same graph, we make a copy of it and then write to it. So any operations that would do something like that follow these semantics. So let's now talk about how do we use Hatchet. So the first thing is it's a Python code. You can install Hatchet by either doing a git clone of that repo and running install. There's a script for installing Hatchet, or you can use pip and just say pip install Hatchet. Once you have Hatchet installed, you can import Hatchet in your regular Python script or in a Jupyter notebook. If you have a directory with the HPC toolkit database, you can use the from. These are static methods defined in the GraphFrame. So you can use from HPC toolkit or from caliper, from call grind. We support many tools by now, so you can use any one of them and then import data. So yeah, here are two examples for HPC toolkit and caliper. If there is a data set that we do not have a reader for, the Hatchet is open source, so we encourage people to contribute readers, and we are happy to help you. It's very simple to write a reader. We just need to organize the input data in terms of a graph and a data frame. So it's fairly straightforward to write a reader and then start using Hatchet. Okay, so once we are able to load data into Hatchet, what are the various operations that that a user can do? So we provide a filter operation. So for example, if you're interested in looking at, in my graph, what are the top functions where I spend most of my time in? So let's say this is your original data frame, and I can apply a filter to it saying, I want to filter by the time column and only look at nodes where I spend more than 10 seconds. So this is how you would specify it. That's the code at the top, single line. And then you get a reduced data frame or a smaller data frame that only has those nodes that match your filter. Now, once you filter a data frame, you have a smaller set of rows. Your graph still looks like it has all the nodes. So we also provide, maybe I'll go to the squash operation first. So we also provide a corresponding squash operation, which goes with filter. So once you've filtered the node and you have a reduced set of data frames, we probably want to remove those nodes in gray that are still in the graph. So that's what the next operation does, which we call squash. It takes the original graph that you had and compares that with the filtered data frame and removes any nodes that are not in the data frame anymore. So basically, it takes children whose parents have been filtered out and connects them to the nearest ancestor. Okay, let me come back to this operation. Now, since most people are running codes that are running on multiple processes, and all of these tools will collect data per MPI process, we also allow you to drop the data per process. So you can use drop index levels, which is saying drop the second index or the third index if it's rank or thread. And you can specify a function you want to use for dropping the rank index or the thread index. So you can say, I just want to keep the max time. What is the max time each rank spends in a particular node? Or you can say, I want to look at the average time spent in each node. So you can use these numpy functions for doing it. So let's say this is your data frame where you have data for 4 processes. You can use drop index levels, and then you only have a single index after that, which is the node. And then your time data is just once per node. That is an average or max, depending on the user supplied function. Okay, now these were some operations that you could do on a single data set or a single graph frame. There are many more operations that are in the manual, so you can look at the Hatchet, read the docs to take a look at that. But now I'm going to start talking about operations you can do if you have 2 different data sets. So let's say I have 2 HPC toolkit or caliber data sets that I read into those 2 graph frames, GF1 and GF2. And I want to look at what is the difference of time I spend in the different nodes when I do these 2 different executions. Now, there are many cases when people do different executions. You might be trying to compare, for example, in NAMD, if I run APO-A1 versus STMV, what is the performance difference? You might be trying to scale your application on different number of nodes and trying to compare as I scale up, how much time do I spend in different functions or call sites, and the subtract operation can look at can help you look at those things. So here's a toy example. Let's say you have a left graph and a right graph, and you spend different times in those graphs, although the color scales look somewhat similar here, but you'll notice that the PSM2 nodes at the bottom are different in the color, or in the color, and correspondingly the time spent in them. Once you do a subtract operation, the Hatchet does a pairwise subtraction of all the nodes matching the unique calling context and tells you what is the difference of time across those two executions. Now, if the graphs are structurally different, we first unify the graphs so that they look structurally the same, and that requires some operations of unifying the graph, matching up the data frames. But once we do that, we can use a subtract on the corresponding data frames. And then for the unified graph, which is on the right side, you can see that if I subtract those two, I spend a lot of time in PSM2 and MPI in terms of the difference. So maybe I want to focus on those as I scale up and see where my performance bottlenecks are. So what I was hoping to do, but I didn't get enough time to work on this, was see if I can show something for a charm example. And I don't have a very interesting case, but I can at least show that things work for charm. So what I did was I took Jacobi 3D from tests under charm. I ran that with 1 VP or 1 char per PE and 8 chars per PE. And let me show you what the script looks like for doing this. So basically, I ran HPC toolkit on those two things. These are the two directories that hold the data that HPC toolkit writes out in the database directories. I load them in from HPC toolkit to GF1 and GF2. I drop the index levels since I was running on multiple processes. Once I drop the index levels, I do a subtract. The filter was not working for some reason. There's probably a bug in Hatchet. But once you do a filter, you can print the graph in the data frame and look at where am I spending my time. So the output here is showing once I do a diff, and this is a terminal output, but we also support many other file formats for looking at the output. You can see the numbers displayed here are the difference in time between those two executions. So I can see that in this function, I spend a lot of time. So red is high, green is low, yellow is somewhere in the middle. For the red or green arrows tell you that those nodes only exist in one of the trees. So the red arrows pointing to the left say that those nodes were only in the left tree. The green arrows tell me that those nodes were only in the right tree. So I can see that these MPI operations were not in the left one for some reason. And so the other thing that Hatchet is useful for, or generally profilers are useful for, are if you're not familiar with the code and you want to figure out what the control flow looks like, it's a good way to figure out what calls what. And since charm is complex, this is a good way to figure out when you start with user code and what are the other things you call as you go through the execution. So this is a simple example where you can take a look at, what are the nodes where I spend time in when I run with different virtualization scenarios. Okay. We provide other algebraic operations. So you can do an add over graph frames. You can do a multiply. You can do a divide if you want to calculate speed up between a run that's running on more processes versus less processes. And you can change the visualization and look at what the result looks like. Also, Hatchet is not a visualization tool. So the ideal thing when you have a large graph is to look at the data frame. So let's say you wanted to look at what nodes do I spend most of my time in. I would probably just print the data frames sorted by time and look at, okay, these are the top nodes where the difference in time was the highest. Yeah, so I already talked about visualization. These are some graph formats we support. We can do terminal output or std out. We can do dot format outputs. We can output to flame graphs. And then recently, we have also added an output for Jupyter notebooks. Now, in the remaining time, I'll try to go over some analysis or sample analysis that we have done using Hatchet that gives you an idea of what are the various kinds of things you can do, which would have required a lot of time staring at a GUI, or it would have required a lot of scripting to do if you were trying to analyze this data yourself. So there's a question from Niels about, can you sort my inclusive and exclusive time? So I'm assuming you're asking about sorting by one of those columns, sorting all the nodes by one of those columns. And yes, you can do that. I mean, some of those operations, so since we use pandas and data frames, you actually have access to the data frame. So any operations that you can do in the pandas API, you can do on the data frame. There are some things that we discourage people from doing that would modify the data frame, because then it breaks the mapping between the graph and the data frame. Of course, you can do them, but then some operations would no longer work once you break that mapping. Okay, so let's say you wanted to look at a gprof type flat profile. So you have a full graph with a calling context, and you wanted to see, I just want to look at what are the top functions in which I spend my time. So you can use the group by operation in pandas. This groups all the rows in pandas by a certain column. So if I use name, it will group all the functions that have the same name and create a single row or single group for them that you can later reduce to a single row, and you can provide the reduction operations. In this case, we're using sums. This will tell you the sums of times I spend in each function by name. And then you can output this. So you can print the data frame. You can sort it by time. Maybe that was the question. So you can sort by inclusive time or exclusive time, and then look at what are the top functions in which I spend my time. If you wanted to identify load imbalance in a given execution, so if you have data for all MPI ranks, you can use drop index levels twice. So you can say, I want to drop my second column in the multi-index, that's rank. Once I drop it by getting the average across all MPI ranks or processes, and then once I drop the columns by getting a max across all those processes. And then I can do a max by mean to look at the imbalance. And again, I can print the data frame or the resulting data frame with the imbalance column. So you can see those are the functions, and this is Lulesh, I think, where I see maximum imbalance across 512 processes. You can also compare two executions. So we have already talked about this. So I'll skip this. You can do a diff or subtract to look at the executions. You can also filter by library. And in fact, recently we have added a complex way to filter by call path patterns. So what I'm showing here is a simple filter where you can say, I want to only look at the functions that start with MPI. So this filters your graphs by functions that start with MPI, and then you can compare those two graphs. Recently, we've also added a functionality to specify call path patterns. So you can say, I want to filter the graph by foo calls bar or MPI calls PSM2, and only look at call paths that match my user filter. So you can use those and filter the graphs in various ways to look at a reduced set of examples. And then finally, I want to talk about one study which can be hopefully done easier than what I did long time ago. So when I was still at PPL in 08, we had this NAMD paper looking at analyzing its performance, optimizing performance and analyzing performance. We looked at trace mode summary logs, which is one of the features in the projections library, to output some high-level summary of time you spent in different functions. These plots were created from those logs. It required a lot of scripting, many developer hours were spent on looking at, if I run NAMD on 1 through 4096 processes or processors, where does my time go up? Where do I spend most of my time? With Hatchet, you can use a few lines of code. So this is showing using the Lulesh dataset that we have running from 1 through 512 cores. You can run a for loop on those datasets, do some simple operations. Then we use a pivot to change how we want to display the data. And you can use, this is about 10 lines of code built on top of Hatchet, and you can print a graph like this. So on the x-axis, it shows the number of processes that I'm running Lulesh on, and the y-axis shows the time spent in different functions. So with a very few lines of code, you can do complex analysis that would have taken many, many lines of code in a tool previously. Okay, so in summary, Hatchet is a tool. It's an open source tool based on Python. It leverages the power of pandas to do performance analysis in HPC codes. And actually, you can use this for Python codes. We also now support various Python profiling tools like cProfile. We are adding a reader for PyInstrument. So you can also use it for looking at Charm for Py performance. We use a graph to index into a data frame, and that helps us do programmatic analysis on hierarchical data. Let's see. Yeah, this says that the implementing a query language is in the future, but it's already implemented now. So if you use the developed version on GitHub, you can get our bleeding edge version. And so there's the link to the GitHub repo and also the link to the docs. So I'll stop here. Thank you, and I can take any questions.